everyone. Today I'm going to be presenting on the paper segment anything, which is based on an image segmentation project that Meta did a few years ago. So this presentation will be broken down into 6 components. First, I'll define what image segmentation is. Then I'll go over the tasks that Segment Anything does, how the data was curated, how the model itself was structured, and an important feature of the model, which was zero-shot learning, and finally, the significance and implications of this project. So first of all, what is image segmentation? Well, image segmentation is the process by which a computer decides which pixels of an image belong to which objects or region of the image. So here, the computer the model took this original image as input and created a segmentation mask as output. So a segmentation mask is basically like a summary image that marks exactly which pixels of the input image belong to which object or region of the image. So for instance, we can see that the model was able to outline the different people in this image and separate them from the background, sky, and ocean. So far, I've been talking about image segmentation as a general process, but it's important to note that there are many different types of image segmentation. For instance, the example that I just gave earlier was of semantic segmentation, which was able to recognize these 3 objects as all humans, whereas panoptic segmentation recognized these different people as distinct. So previous image segmentation models could only conduct specific types of image segmentation, and they were task specific. For instance, a previous model could only do object detection or could only conduct edge detection and detect the boundaries between images in an image. These previous models also needed to be trained on large human-labeled data sets. So what that means is humans had to label image masks themselves to create these data sets, which was too time-consuming and costly. On the other hand, SAM, or the Segment Anything model, effectively handles these problems. First, SAM can conduct many different types of image segmentation instead of just only one or a few types. Second, SAM is also trained on a model-in-the-loop dataset that does not require as much human labeling as previous models. So SAM can be broken down into 3 components. First, task, then model, and data. The first part, the task, is given by a segmentation prompt that tells the model what should be segmented. And so one important distinction between SAM and earlier models is that it can handle ambiguous tasks where the prompt is unclear. So for instance, SAM can handle uncertainty in point prompts. So in this column to the right, it might be hard to see, but you can see that there's a point on the Z in Zurich, and the model may not know whether the user wants to segment this entire block here, the entire word Zurich, or just the Z. And there also may be uncertainty in text prompts. For example, if a text prompt tells SAM to segment the kangaroo, SAM might not know which kangaroo to segment. And in the case of ambiguous tasks like these, SAM will return one valid segmentation mask, for one of the possible objects that the prompt may be referring to. And we'll go into more detail about what the prompt looks like in the next few slides. But first, let's talk about the data used to train SAM. So previously we mentioned that there's a lack of accessible training data available. So to counteract this problem, the researchers used a model in the loop data set. So a model in the loop data set is a data set in which the model is involved in the process of creating training data that could then be plugged back into the model. The creation of this model in the loop data set was separated into 3 stages: assisted manual, semi-automatic, and fully automatic. And in each stage, humans gradually have less involvement in the curation of the masks. Using this strategy to generate data, the researchers were able to generate 1.1 billion high-quality masks from just 11 million images, and around 99.1% of the masks generated were created in the fully automatic stage of data curation. So humans were barely involved in that stage. Now I'll go over how the model that actually does the image segmentation works. So the model architecture can be broken down into 3 main components: an image encoder, a prompt encoder, and a mask decoder. An encoder processes the prompted task in such a way that the computer can understand what it needs to segment. And the decoder creates a segmentation mask that combines the outputs from the image and prompt encoders. So first, the image embedder the image encoder is responsible for creating an image embedding, which is basically like a summary of the image we're focusing on. Second, the prompt encoder encodes sparse and dense prompts into an output called the prompt embedding. Sparse prompts include points and boxes on the image or text, and point and box prompts are positionally encoded on a map by the prompt encoder. Text prompts are encoded by CLIP, which is a text transformer, and dense prompts or segmentation masks are embedded using convolutions. And finally, the mask decoder uses a modification of a transformer decoder block to combine the image embedding, prompt embedding, and an output token to create the final segmentation mask. So another important feature of this model is that it's zero-shot, meaning that you don't need to train the model on a new data set for every new task that hasn't been trained on before. In other words, the model can be used out of the box and can handle many different types of tasks. So for instance, in the image to the right, we see these 2 original images fed into the model, and the model was told to do edge prediction. And SAM had previously not been trained to do edge detection, but it was able to do it pretty accurately. So this column here is for the ground truth, or like the actual edge detection mask, whereas this one is what SAM did, and you can see that they're pretty similar. And also, so SAM is also pretty accurate. So here we have 2 graphs. On the y-axis we have MIOU, which stands for mean intersection over union, and mean intersection over union compares the predicted mask by SAM to the actual mask. And these 2 graphs compare SAM to other models, and as you can see, the orange line representing SAM is generally above the other lines, which shows how SAM consistently outperforms other models. However, SAM does come with a few limitations. First, it can miss fine structures like the umbrella here. It can hallucinate small disconnected components, and it doesn't produce boundaries as crisply as other models might. So why is SAM significant? Well, SAM is unique because it can perform segmentation based on prompts that require little effort on the part of the user. SAM is also something called a foundation model, meaning that it can handle a variety of tasks and a variety of different prompts without having been explicitly trained to do so. So as for how SAM might be used, it can be used in different fields like scientific research for medical imaging and being able to distinguish, for example, if a skin lesion is cancerous or not. It can also be used in creative editing, so for video and photo effects, or autonomous vehicles, so that they can see which objects might be vehicles, pedestrians, or street signs. And it can also be used in e-commerce in product photos. So far, I've been talking about the first SAM model that's Meta released, which masked a single object in an image. But recently, there have been updates made to SAM. So for instance, SAM 2, which was released in July of 2024, masks a single object in videos. SAM 3, which was recently released, masks multiple objects in videos. So currently Meta is working on a SAM 3D model that can interpret 3D space. And furthermore, in the future, more domain-specific models, such as those for satellite imaging or interior design, will hopefully draw inspiration from the innovative design of the Segment Anything model. Finally, I'd like to thank the Journal Club staff, so Lucas, Eric, Arjun, and Charlie, and thank you Mr. Maxwell and all the teachers giving extra credit. Dr. Sidorsky.
Yes, so at the beginning you said that you don't need so much manual input for the data. Is the automatic is just based on previous models, or how is the automatic segmentation?
Could you elaborate on that question?
So you have a slide that says that you can have like user doing the segmentation, or you can have automatic segmentation. And one of the advantages here is that you don't have to have so much user defined.
Yeah.
Right? Is the automatic segmentation based on previous models, or how is that done?
Yeah, so I guess I can talk a little bit more about the model architecture. So previously I was mentioning that the model is made of two encoders, so an image encoder and a prompt encoder, and then a mask decoder. And the image encoder uses a vision transformer. So you may have heard of text transformers. So an image or a vision transformer basically takes different parts of an image and determines the relationships between those parts. And then we also have a prompt encoder, and the dense masks uses convolutions to create a prompt embedding. And yeah, I don't know, does that answer your question?
I was talking more about the training data. You said that the training data can be automatically related to that, yeah.
Oh
That
yeah.
last column, is that done in previous model?
No, it's done with SAM itself. Right, the fully automatic is done with SAM itself.
Yeah.
So it's SAM training itself.
Yeah. So it's like a model in the Leaf data set, like where the model SAM is involved in creating that data. Christian.
Yeah, thanks for the presentation. So I'm curious why, if you have an idea of why they decided to treat points and boxes as prompts differently than input masks, because it seems to me that you should be able to treat them the same if you look at them as like probability masses and then apply a sort of optimal transport problem to move that mass to the target mass.
I'm not sure, but
Can you repeat that?
Yeah, just why did they, or give an idea of why they treated points and box masks inputs differently than like full masks? Because they pass the point and, or at least the slide on the architecture shows they pass points and boxes as inputs of a prompt encoder, whereas they pass masks to a different mask encoder.
well, I think like the points and boxes are like the sort, like they're handled differently because like I'm not really sure.